Well, hello. Good evening, everybody. Hi there. My name is Kim Ryder, and I'm the Director of Operations here at the Wayne Theater. On behalf of our Board of Directors, our amazing ambassadors, and our staff, we welcome you here to the Wayne Theater. It's going to be a great night. What a wonderful and interesting lecture this will be. So you're definitely in for a treat, as you well know. But before we get started, I just want to tell you a few things that are coming up here at the Wayne. This week, Thursday night, we have Good Shot Judy, an awesome band. They are a swing band with vocalists and brass and all things that make us want to dance. So come and join us for that. Friday night, we have Empire Trio, and they are vocalists. They're going to sing Broadway tunes and or movie themes, so that's going to be a lot of fun. At the end of the month, our big treat for the holidays is Elf, the musical. It's going to be on stage for 2 weeks, guys, and also, just for a fun little tidbit, it is the 20th anniversary of the film. So that was quick. So we're embracing that as well. We have Pam Tillis later on in December. We've got the Rush Experience, Merry Country Christmas, all kinds of great things coming to the Wayne. So please help yourself to brochures we have out front, and of course always visit our website for more information. But without further ado, I would like to introduce Mr. Joe Kuiper. He's that guy right there.
Hey, good evening, everybody. Yeah, I'm Joe Kuiper. I'm director of the Virginia Museum of Natural History. Hey, how many of you have seen that there's like a trailer down at the lot there at Arch and Main? Yeah, it's got VMFA all over it, right? So what's the story behind that? VMFA, the Virginia Museum of Fine Arts, they've had this Artmobile, which is an incredible program that we as Virginians should all be proud of. They have brought this via tractor trailer, a mobile exhibit experience all around Virginia. I've seen it in Bristol, I've seen it in Martinsville, it's been up here in Waynesboro, and it's been there to teach students and families and educators about the wonderful stories of art. And as such, they've been to 350 different locations with it. Well, you know, they decided they're going to get a new one. Well, thanks to Senator Emmett Hanger and the General Assembly, we have just absorbed that and moved it over to the lot at Arch and Main. And so you're going to see some transformations there. Now, let me digress a little bit here. For those of you who've known me, you might be a little concerned. You might have noticed I'm a little more gray, right? But don't worry, it's no problem. It's just spackle, right? You know, we've had to do some improvements. We've been doing a little painting. We've been doing a little spackling. It gets in my beard and makes me look a little older, but it's all right. So what's going to happen is on December 9th and 10th, we are going to participate with the city of Waynesboro in an LL Bean pop-up event. In other words, they're going to bring a store right here to Waynesboro at the corner of Arch and Main, at the lot there, right where the trailer is. And at that point, we're going to have it open publicly for exhibits. So it's not going to be a huge exhibit experience, but it's going to be a fun exhibit experience. We'll have people in there. We're going to be putting in some exhibits that are pertinent to the Waynesboro, Stanton, Augusta County general region and so forth. So it's going to be kind of attractive and so forth, and LL Bean will be there. On top of that, on December 8th at noon, right there, we're going to participate in a ribbon cutting with the Greater Augusta County Chamber of Commerce. So please come out for either of those. The December 9th and 10th event will be all day long. Look on the Chamber's website and the city's website for it. And so this is just one more step forward in our establishment of a branch here in Waynesboro. You've been hearing me talk about this for a long time. So we have checked all the boxes that we can as a state agency. We have met with the governor's staff. We have worked with local legislators and so forth. What we need from you, our call to action, and we did this last month and the month before this with the lecture series here at the Wayne Theater, is contact your legislators, regardless of where you live, whether it's Delegate Runyon or it's Senator Hanger or Delegate Avoli, right? We have Senator Campbell going to be taking over this area. We have incoming Senator Head going to be taking over this area. We have other colleagues over the mountain. We have Senator Deeds, who have all been very supportive. There's been no opposition to this. Everyone thinks that us having a 28,000 square foot branch campus that has exhibits on the region in which this city exists that will draw people from the Shenandoah National Park and Blue Ridge Parkway. No one has any opposition to that. It is a great thing. It's a great two-way story. One, it's an economic development and a cultural development project for this region, but it is also an opportunity for our agency to reach new audiences and teach people about the wonderful natural history, the natural wonders of the world that exist right here within the Shenandoah region as well as the Blue Ridge. So that's what we're doing. And we couldn't do what we do without the folks that help us. First of all, I want to point out, have you all heard about the new economic development news here through Waynesboro Economic Development? Has anyone not heard about what the new, I hear a little buzz there, right? So yeah, you know, economic development and the city of Waynesboro has attracted the attention of Northrop Grumman, a major industry, and they're going to be putting in a plant right here on the north side of Waynesboro, right? And that's going to be a 300 job situation that should be finished by 2025. It's a major accomplishment for everyone. And you know what? Us opening a branch at that point, at this point in history, is going to be very complementary. In other words, we're going to be providing not only the educational aspects of our operation, but also we will be providing the quality of life for the people who are recruited to work the jobs that are there. So there's so much going on within this region. We're so proud to be a little part of it, and we're looking forward to kind of blossoming here up in the next couple of years. But it's, again, I'm going to come back to you. We've got to reach out to the General Assembly. We've got to reach out to our elected officials and make sure that they know that everyone supports this. I'm wearing short sleeves for a reason, you know, right? Sometimes I wear long sleeves and I roll them up, but whatever. You get the idea here, right? The staff of the Virginia Museum of Natural History is ready to roll up its sleeves, establish the branch here, serve the people, the educators, the students of this region, be an economic development driver for tourism in the region. And so we want to continue to be part of that. And this trailer that we have here with our pop-up event that we'll participate in on December 9th and 10th. We hope to see you all there. We think that will be just one step closer to bringing this full branch to reality. Now, all that said, I want to thank the South River Watershed Coalition, great partners in doing everything that we do here. I want to thank them for that. Center for Cold Waters Restoration have been with us ever since the very beginning, and as well as the Wayne Theater and all the great lectures we've done here. And I want to thank everyone who is online tonight. We have had such great participation with our social media and web media as far as engaging people remotely. So that being said, we've got a great lecture tonight. It's going to be a great complement to the other lectures we've had here on a number of different topics related to natural history. We have Matt Heller from Virginia Energy, right? This is an organization that is all about our natural resources and how we utilize them and conserve them. We have worked as an agency with Virginia Energy on so many occasions. Back during the time they were called the Virginia Department of Mines, Minerals, and Energy, right? Yeah, it's kind of hard to make that transition, but Virginia Energy is continuing to be a huge part of our natural economy and so forth. So Matt has been a member of this group for a very long time, and I'm also very proud to say that he has volunteered his time to work with me and to work with museum staff to develop stories of geological interest that will be part of the permanent exhibits of the Virginia Museum of Natural History Waynesboro campus. And so without any further ado, let's go ahead and give a warm welcome to geologist Matt Heller, who will be speaking to us tonight. Matt, it's all yours.
All right, thank you for the warm welcome. Again, Matt Heller, Virginia Department of Energy. I really appreciate the opportunity to speak to everyone here tonight. Thank you for coming out on a cold evening. What I want to do tonight really is connect two things, rocks and people. And the way I'm going to do that is the title here, by talking about how geology influences our lives here in the Shenandoah Valley. I like talking about the geology all around Virginia, but I'm particularly excited to talk about the Shenandoah Valley's geology for a few reasons. One is that I learned about geology here in the Shenandoah Valley as a student at James Madison University. A second reason that I want to talk about this area, and I enjoy talking about it, is that I've lived in the Shenandoah Valley for about half of my life. My wife and I have been in the Fishersville area for the last 20 years, so not only do we walk around here at work, but we live here in this area. And in addition, I've been at the Virginia Department of Energy about 20 years, and roughly about 50% of the mapping and other project work. Are you all not hearing me okay?
I'm having trouble hearing you, just me maybe.
Oh, okay. Can you folks hear me okay in the back? Oh, okay. I apologize, sir.
We can hear you okay, Matt. Maybe just bend the microphone a little closer.
Okay. I will try my best to do that. Okay. All right. Well, very good. Anyway, the third thing I was going to mention is that I have done a fair amount of work right here in the Shenandoah Valley. About half of the work that I've done over the last 20 years has been focused on understanding the geology of this part of Virginia. You okay? Good? Okay. So first thing I want to do is kind of define the Shenandoah Valley just for the purposes of the talk tonight. And really, we're going to be talking about the watershed that is drained by the north and south forks of the Shenandoah River here. And I apologize, it doesn't look as clear to me on the screen there as it does on my computer. But for tonight, we're going to be focused mainly just on the Virginia portion of the watershed. And you may know, if you live in this area, that there are two major provinces within the Shenandoah watershed here in Virginia. To the east in blue is the Blue Ridge Mountains, of course. And to the west in this, I don't know what color you might call that, peach or tan color, is the Valley and Ridge province. But for tonight, I want to dig into a little bit more detail with the Valley and Ridge, and I'm going to subdivide that into three sub-provinces. Four sub-provinces. So to the west in purple here is what some geologists refer to as the Ridge and Valley province, because there are more ridges than there are valleys. And the eastern edge of that is defined by Little North Mountain and some other ridges in this part of Virginia. And then in green, of course, is the Massanutten Mountain area, those of you who are familiar with that area. And it's also a rugged area, like the Ridge and Valley, and it actually shares a lot of characteristics, these two sub-provinces. In this lighter color, there's a lower relief area, and that is the Shenandoah Valley proper. Of course, we're situated down here within that part of the valley. And locally, between Massanutten and the Blue Ridge Mountains, that's sometimes referred to as Page Valley. And then this area here may be a little less familiar to many of you, this sort of orange-colored area. Geologists refer to this as the Western Toe. So this is an area where a lot of material has been shed from the Blue Ridge Mountains to the west, and it creates some unique landforms, relatively low relief, but it's a predominantly wooded area, and it has some different characteristics, so I decided to break it out here as its own thing. You may know, I'm sure many of you know, that people in the Shenandoah Valley have been connecting with each other for quite a while. Archaeologists have identified evidence of indigenous hunters in this area more than 12,000 years ago. Hunter-gatherers lived seasonally in the valley, we believe, between about 11,000 and 3,000 years ago. And then between about 3,000 and 500 years ago, we had more extensive and permanent human settlements here in the valley, including some settlements very close to where we are today. And these indigenous people really are the first owners and residents of the area that we're in today. European settlement began in earnest about 300 years ago, and we've done a lot of settling. We have more than 400,000 people in the area that we call the Shenandoah Valley today in Virginia. So you might have a guess that rocks go a little further back than people, and I would say they go way, way, way back here. So the oldest rocks in Virginia are about between 1.2 and 1 billion years old, quite a bit older. And those are in the Blue Ridge province, so along the eastern edge of the valley. And the colors, I'm sorry, aren't coming out that well, but sort of these grays and tans are some of the older basement rocks in this part of the Shenandoah Valley. These rocks are overlain by both volcanic and sedimentary rock layers in the Blue Ridge and also to the west in the Valley and Ridge Province where we are today. And all of these different colors shown on this, go back up here. All of these different colors shown on the map here are different distinct types of rock. And together the sedimentary and volcanic rocks span more than 200 million years of Earth's history, and it also bridges a major time interval boundary between the Proterozoic and the Paleozoic eras. So it's been a place of research and study really for more than a century. We have here and there in the valley younger intrusive rocks that were originally magma, and they're illustrated by these little red lines here. Okay? And notice that they predominate in the southern part of the valley, which is kind of interesting to me. I'm not exactly sure why that is, but, but that's just the way it is. And then here and there, on top of the, all of the bedrock, we have these deposits of loose material, and you can see these various colors here scattered throughout the valley. And there are deposits of gravel and silt and sand and clay. And we'll talk a little bit more about why they form. But in terms of their age, they range from material that's as old as 8 million years. We actually dated some sediments down in this area to material that's being deposited right now, you know, in the modern streams as they're flowing along. I would say that most of the material is probably less than 1 million years old. What I'm going to highlight today, and I guess one of the reasons I really wanted to give this talk related to the Shenandoah Valley is that the natural conditions here are so variable. We have so many different types of rocks, so many different processes have been active here in the valley over a really long time. It creates very distinct and unique areas, you know, that vary from place to place. And I'm sure many of you who live here have experienced that and are familiar with the diversity of our landscape and our ecosystems and our rocks, et cetera. So the kind of the message I want to send here today is that the natural conditions in the valley result from processes that are occurring within different Earth systems. This is a diagram that I lifted from the internet, but it shows different Earth systems in spatial relationship to one another, and I just want to highlight what those systems are. You may not think about the atmosphere when we're giving a geology talk, but remember our climate and weather and rain come from the atmosphere and wind, you know, and that has effects on the rocks below. The biosphere is another Earth system, and that's us, you and me, and every other living organism that calls the valley home. The pedosphere is the soil that we dig into, that we grow our food in, that we build our structures on. That's another important system. The lithosphere, of course, that's we're going to be seeing a lot of that tonight in this talk. That's the underlying bedrock. And then the hydrosphere, so that's the water vapor in the atmosphere. It's the water in our streams, rivers, and lakes. It's the water beneath our feet, the groundwater, and we'll see some examples of how groundwater and geology connect later in the talk. The area where all of these different systems interact, and you know, this area where we live is known by this name, the critical zone. And it's because, of course, the things that happen here are really important to us, and it's from our perspective. And I believe the museum is actually considering using the critical zone as a theme in some of their exhibits, so that's kind of exciting, and I wanted to introduce that if you weren't familiar with that term tonight. So we're going to be focusing on some processes and how they relate to the geology here in the valley. So the 6 processes that I want to talk about are magmatism, okay, and that's basically the intrusion of molten material into bedrock that would then later cool and turn into a brand new rock. Deposition, and deposition is a process that is basically the accumulation of sediment, which is loose rock material, and maybe one day that sediment might become a rock. Metamorphism is change that occurs in rocks due to the application of heat and pressure. Deformation is a big word, but it relates to changes that occur in rocks when we squish them, when we push them together and cause physical stresses to the rocks. And weathering is another really important process that involves the physical or chemical decay of rock and really the creation of soil, but also the continued weathering of soil. And weathering, in this region, a humid climate that we're in, is primarily, primarily related to water interacting with the materials, but also air, roots of plants, etc., can cause weathering to be accelerated. And then the last process is erosion. And erosion, the difference between weathering and erosion happens and involves transportation, whereas weathering happens in place. It's an in situ process. So erosion is the physical or chemical removal of rock or soil, transportation of that material somewhere else, and then eventually, in most cases, redeposition. So these are related processes, erosion and weathering. And so most of the natural conditions we're going to be talking about in the remainder of the talk don't just result from one of these. Okay? They result from multiple processes. This is a dynamic system, a lot of interrelationships going on between these different processes. I mentioned, the valley being a place that has so much distinct and unique and different characteristics, and that's because we have a lot of variations in the processes that I've just identified, and they create these distinct conditions in different parts of the watershed. And I'm going to be showing you some examples of those with photographs as we go forward. But the first thing I want to do is kind of go back to this diagram of the different provinces in the valley and just describe in general how these different provinces relate and are different from one another. So the ridge and valley, that purple area to the west, is dominated by rocks that are resistant, predominantly sandstones, and rocks that are less resistant, predominantly shales. And that sets up these very different landforms, these resistant ridges and these really deep incised valleys. Okay? In the valley, in the Ridge and Valley province, in the eastern part of that province, the folding is pretty intense, but as you go further west, the folding gets less intense, and you can see the difference, I think, reflected in the landforms as you go from east to west in that area. The Great Valley, of course, this area, is dominated by a group of rocks called carbonate rocks that include limestones and a similar rock called dolomite, and shales. And that's one of the reasons there's this big wide valley here. We have less resistant rocks in the central part of the watershed. We do have thin resistant units that are comprised of rocks like chert, which is a silica-rich rock that's very resistant to weathering, and sandstone that is also resistant to weathering. And that creates ridges and hills, and you can see some of those. It's a little blurry on here, but some of these distinct ridges and hills, we'll see those in more detail a little bit later. They create the landscape that we see within this part of the valley. And I also need to mention these igneous dikes. They're also more resistant to weathering than the surrounding sedimentary rocks, and so they create positive landforms as well. The Massanutten Mountain province contains rocks that are similar in age and characteristics to the Ridge and Valley province. But the sandstones, particularly the one that makes up the big ridges here in Massanutten, is much thicker. The Massanutten sandstone is about 500 feet thick, where the sandstone that makes up this ridge, the Tuscarora, is probably about 50 feet thick, so much thicker, and that's why the ridges here are much thicker. It's reflecting the geology. The other thing about this part of the valley is that these rocks are intensely folded in here, and so that's another reason it has a bit of a different topography developed on it. The Blue Ridge over here, again in the east, contains rocks that overall are more resistant to weathering than rocks in the Valley and Ridge province. That's one of the reasons we have a big mountain range here. In addition, you don't see the sort of layering, right, in the folding patterns that we have in here over in this area. And these rocks, at least the what we call the cover rocks, the ones on top, are folded, but the folding is a bigger, broader fold, at least in the big picture here. And what we call the basement rocks, the older rocks down here, aren't necessarily folded, so they don't express that pattern that you see out in the valley and ridge. The western toe here, it's situated at the boundary between the Blue Ridge and the Valley and Ridge rocks of the Great Valley, and so that sort of difference in weathering creates this gradient here, right? And that encourages material to be shed from the high places into the low places. And the deposits that occur down here we call fan deposits, and they're coarse, loose deposits of sediment, and it really just creates a distinct area, and it's related to the fact that the bedrock in most of this area is not actually at the surface, it's underneath of loose material that's been shed from the mountains. Okay, so now I'm just going to go through some photographs that illustrate some of the different processes we've been talking about, some of the different rocks that we find here in the valley. This is one of the older basement rocks. This is the Old Rag granite. How many people have heard of the Old Rag granite? Or the Old Rag mountain, at least. Hopefully some of you have. Yeah, that's a mountain, but the granite actually extends over a much wider area than the mountain itself. But it's about 1 billion years old, just a little bit over 1 billion years old. And it looks just like a granite. The neat thing about the Old Rag and a lot of the basement rocks is that the quartz in this rock has a bluish color. And we only see that in the older rocks in the basement. We don't see those blue quartz grains in younger igneous rocks in Virginia. This rock is a volcanic rock, so both of these are related to magnetism. One deeper in the Earth's crust, cooled slowly. One closer to the Earth's surface, cooled much more quickly. This is a basalt, but it has been changed. It's been metamorphosed. But you may notice, if you look closely, a lot of little round spots. Okay? When you have a volcanic eruption and lava is flowing on the ground, there's a lot of gas that's flowing along with the lava, and that gas is trying to escape up through the molten material as it's cooling. Well, not all of that gas escapes initially, and so it gets trapped as the rocks cool, and then it leaves behind these little voids, vesicles. And then later, other minerals come and fill those voids in. We call these amidules. This greener material is a mineral called epidote, but we find quartz and jasper and other materials in these little vugs in the basalt. This is a younger igneous rock. This is a dike, so a planar feature that cuts across the older bedrock. And it's a basalt as well. But when we map the dikes, we tend to use this other term here called diabase. So this is in the valley, this is like finding a needle in a haystack. This bedrock comprises probably just a fraction of a percentage of the total bedrock out there, but it's very distinct and different than the rocks around it. This is another basalt. This is actually the youngest igneous rock that I'm aware of in eastern North America. It's about 50 million years old. It forms in the vicinity of Mole Hill near Harrisonburg, Virginia. And you might see some similar textures to the Catoctin basalt that I just showed you a minute ago. But this is a really neat feature. Mole Hill is a positive feature in the landscape, and it exists there because the basalt is more resistant to weathering than the carbonate rocks that are around it. Now I'm going to show you some of the sedimentary rocks that form as a result of the process of deposition. This is a thin layer of sediment in the Blue Ridge province that became a sedimentary rock. It is what we call a conglomerate because it's got pebbles in it. Okay? But mostly it's composed of sand-sized material. It actually has blue quartz in it, and that's because this rock formed as a result of the erosion of the older basement rock, like the Old Rag granite, and then the deposition of that material in a low spot, likely on this landscape that existed at that time. So that's a good example of a sedimentary rock there. This is another sedimentary rock in the Blue Ridge province. This is the youngest sedimentary rock in the Blue Ridge province. This is called the Antietam quartzite. It's a really distinctive rock on the landscape. It's composed of about 98% quartz sand. And so undoubtedly the environment that this rock was deposited in was a beach environment. And I always, when I talk to school groups and kids, I like to point out the fact that the beach is up here in the mountains, and just that's kind of a neat, thing for them to think about, right? Like, how did the beach get up in the mountains? So kind of a neat idea. But this rock's about 540 million years old, so it's really just about right at the Cambrian, pre-Cambrian boundary. So this major break in geologic time. And there are fossils in this rock called scolithus. They're these little worm tubes. that existed, the worms existed in the beach that existed at that time. And when you start seeing them in rocks around, you can't unsee them. There literally must be trillions and trillions of these little worm tubes all over the place. It's amazing. So anyway, that's a good example of a Blue Ridge sedimentary rock. This is a slightly younger sedimentary rock. It's still Cambrian in age, but it's called the Waynesboro Formation, and it consists, roughly 50% of it is limestone, or this similar rock called dolomite, but the rest is shale or thin beds of sandstone. It often has a reddish color to it. You may be able to pick that up in this photograph. But this is actually the bedrock. If we were to go outside right now and start digging holes and got down to the bedrock, we would be in the Waynesboro Formation. And you might say, hey, that's pretty cool. Waynesboro, Virginia has a formation named after it, right? But unfortunately, this is actually named for a town in Pennsylvania, Waynesboro, Pennsylvania. What are the odds, right? That two towns, same name, same rock is underneath of both towns. Pretty cool. That's not the only example of that, so it's really kind of funny. This is the next layer up from the Waynesboro. This is the Elbrook Formation. It's a magnesium limestone. The neat thing about this one is it commonly has a fossil in it. These are what are called stromatolites. So these are layers of algae that alternated with sediment. This would have been in the tidal zone where the water was coming in and out, and the algae were essentially building up through the sand as it was being deposited, or not the sand, but the carbonate mud. And then over time, that lithified and became a rock. This is a younger rock. This is from the Ordovician period. This is called the Lincolnshire limestone, and it's distinctive because it has these little chert nodules in it, and that makes it more resistant to weathering. So when we find the Lincolnshire, typically we find it up on hills and ridges because it's just a little more resistant to the weathering, and it doesn't take much, just 50 feet of a little bit of chert here and there creates a difference in the weathering and the landscape. This is a different kind of sedimentary rock. This is a sandstone. This is the Massanutten sandstone. It's pretty clean sandstone as well, but it didn't form at a beach. This probably formed in a river type setting. And one of the neat textures you can see here, if you see how the partings here kind of have a curved appearance to them here and there. So these are old river channels, and so the water was moving back and forth and just cutting back through its own channel over time as it migrated back and forth. This is a similar deposit. It's also a pretty quartz-rich sandstone called the Ridgely sandstone, but the difference is this one is Silurian in age, and this one is Devonian, so it's a bit younger. The other difference here is you see these little pock marks. These are molds where brachiopod fossils formerly were, and the brachiopods weathered out preferentially because they're made of more soluble material. And so the sand is left behind, but the fossils have vanished over time. This is another type of sedimentary rock, kind of a mix, really, of one we have talked about, sandstone. These are sandstone layers. But then shale. This is the first shale I think I've showed you tonight. So this is interbedded shales and sandstones. This is a marine deposit, so this would have been in deeper water offshore, probably in a deltaic environment, relatively deep basin. A lot of energy washing material out to sea periodically. This is also Ordovician in age. This is the type of bedrock that's in the Fishersville area between Fishersville and Stanton on 250. Most of the rocks you'll see there are shale and sandstone of the Martinsburg Formation. This is a younger shale. This is Devonian in age also. This is called the Millboro Shale. It's a black shale, makes a really poor soil. I'll show you a picture of that in a minute. And it's most commonly found west of Little North Mountain, out in the Ridge and Valley part of the province. All right, so the last pictures I want to show you are of not rocks, but loose material that's deposited on top of rock. This is a colleague of mine, Scott Eaton from JMU. And this is a nice photo because it shows the boundary between bedrock, so between the lithosphere Earth system, right, and this loose material, which it would be the pedosphere, okay? And so this is a transported soil, but you can see these loose boulders here with finer grained sediment in between them. This is a high energy deposit of material flushed out of a steep sloped mountainous area here. So just to give you some examples of the kind of deposits, this would be a talus or scree slope here. This is down near big levels, but there's a really great talus slope at Shenandoah Lake. If you're interested in that, you can get to pretty easily from the dam side of the lake. This is a debris flow deposit. I don't know if anybody was here when Ann Witt gave a presentation about a year ago. Oh, good, at least one person. She talked a lot about landslides, and the most common type of landslide, well, maybe not the most common, but the most concerning type of landslide here in this part of Virginia are debris flows. And these are rapid movements of rock and soil and trees and water during heavy rain events. And this is my walking stick here, so this gives you a sense of the size of this boulder. But these boulders are more than a mile from the nearest outcrop of this formation. So that's a lot of energy, right, to flush material out that distance. But that's a common type of loose deposit that we have here in the Shenandoah Valley. This is what we call an alluvial deposit, but I'll just call it a stream deposit here. So this is mostly silt and clay and a little bit of sand deposited. There's a small stream just out of view here. It's the floodplain, right? So we have many deposits like this along our streams and rivers in this part of the valley. This is an older floodplain, but actually this is the channel, the old channel, because you can see all these cobbles and things in here. This is what we call a terrace deposit. So often in elevated slope positions above rivers and near rivers, we find these gravels, and they're places where the river used to be, back at some point in the distant past. And over time, weathering and erosion have removed the floodplain deposits from the top. So often we just see the channel deposits right at the ground surface in these older terraces. Metamorphism, just a couple of examples here. So this is the Catoctin Formation. Again, this is originally would have been a basalt. It would have had the minerals pyroxene and feldspar as the predominant minerals. But now it has a mineral called amphibole, a particular type called actinolite that's a green color to it. It also has chlorite, which is a mica that has a greenish color. And then it's a little hard to see, but this part of the rock has a mineral called epidote that's also green. So that's why the greenstone, you may have heard of the Catoctin greenstone, that's why it's the greenstone, because of metamorphism, it's changed the color. The original rock would have been closer to a dark gray or a black color. Metamorphism can also impart a texture to rocks. You can maybe see these interlayered darker and lighter intervals here. The lighter intervals are mostly quartz and feldspar, and the darker intervals are mostly micas and some other iron-rich minerals. And so often when rocks are metamorphosed, there's what we call segregation that occurs, and the minerals will segregate into different banded colors here. So this layering is called a foliation. And I think it got that name because it reminded people of leaves, like laying down in the forest. So. A few pictures of deformation here related to the squishing of the rocks, the pushing together of the rocks, mostly through plate tectonic activity. This is the Martinsburg Formation. I've showed you a picture of the Martinsburg already, but here we're seeing two different fabrics. Okay, the beds of the sediment are in here like this. Okay, so that's the way the bed's kind of in the same direction as the hammer. But if you look very close, you see this really strong kind of vertical fabric, right? A grain to the rocks. That's called a cleavage, and a cleavage is a plane that develops when the rocks are pushed together. It develops perpendicular to the direction they're being pushed. And this becomes important when we start talking about water moving through rocks, because water moving through rocks provides us with our drinking water, right, for a lot of us. So knowing something about those cracks and crevices that the water can move through is kind of important for that. This is a mud, did it again. This is a limestone. We actually call it a lime mudstone because it's kind of a mix of lime and mud, but it's a formation called the Edinburgh Formation. It's the same stone that JMU uses for campus, the blue stone at JMU. But the reason I'm showing it here, if you see these little cracks in the rock that look like they've been filled in with caulk, so that caulk is calcite, a mineral that comes in. So this rock during deformation experienced the stress of tension, and it pulled the rock apart here and there. You can actually see what they call tension gashes right here. But that's the evidence of deformation too, if you see that sort of thing in a rock. This is another piece of evidence we look for when we're looking for, did rocks move? Is there a fault nearby? These are called slicken lines. They're these sort of striations on the rock. We often see them where two rocks have slid past one another, and it helps us because it tells us kind of the direction that they slid, right? So that's good. This is a rock called a breccia, and so it's just broken up bits of rocks that have been re-cemented together. And so this would have been along a fault, where the rock layer got broken, and then later fluids came in and deposited other materials that cemented the rock back together. We have lots of folds in the Shenandoah Valley, and that's expressed in the topography. This is a fold, an upfold that we call an anticline here. This is in a shale unit, and the center of the fold is kind of right through here. And again, you see that really strong layering. That's the cleavage. So when rocks get squished, they get folded. Often, especially the finer grain rocks, develop this really strong cleavage to them. Here's a sort of a map pattern fold. This is looking at the ski resort at Massanutten here from the northwest. This is the Massanutten sandstone coming along here. There's a little gap right here, which we'll talk about again in a minute. But you can literally see the rocks being folded around, and that's one of the reasons there's a ski resort there. You've got this nice north-facing slope, that keeps it a little bit cooler in the wintertime. This is a fault. We also have many, many faults in this part of Virginia. This is in a quarry near Broadway, Virginia. And the orange line represents the fault. This is what we call the hanging wall. It's on top of the fault, the foot wall. If you look really close, you might see a little bit of bedding right down here. So all this white in here is calcite fracturing. So that when you see something like that, wow, that rock's really been messed up. And it's been messed up because all of these rocks have been pushed way up over the top of them. This is another fault. It's a little more subtle here, this boundary that I'm pointing to. This is a Cambrian age rock that's sitting on top of an Ordovician age rock, and the problem with that is that's upside down. Things should get younger when you go up, and so that tells us that there's a pretty big fault here. This is actually a fault called the North Mountain Fault, which is the bounding fault for the Great Valley province on the west, so it's a pretty significant structure in this part of Virginia. Some examples of weathering and erosion. Here's the same Massanutten area. This is the Massanutten sandstone outcropping. Again, it's a quartz-rich sandstone, pretty resistant to the process of weathering and erosion. So over time, it tends to form these resistant ridges on the landscape. And it's really nice to be able to see those when you're standing and looking at them. This is another pretty resistant rock. This is a rock called chert. It's rich in silica. Doesn't react with water that well, and it's pretty strong, so it sticks around for a while. Many of the sort of roundish hills that we have out in this part of Virginia are what we call chert hills. This is actually Betsy Bell in Stanton. So when you're driving towards Stanton on 250, that big hill right in front of you there, you drive up to the top of that at the park. There's a bunch of chert sitting up there. So. Just a couple of examples of shale valleys. So this is a place called Fort Valley in the northern part of Massanutten. And the unit that's in the middle here is shale. And that's why this is a low area in the middle. The unit that's sandstone is the more resistant unit. So creates that nice valley in that area. And then just a second example of that. This is, I was mentioning the Martinsburg between Waynesboro and Stanton. This is the Martinsburg in here. This is Christians Creek that runs up through the middle of this fold. This is a big, an upfold that we call a syncline within this area. I guess I should point out here too, just because it's so cool, this is the North Fork of the Shenandoah River. This is the South Fork of the Shenandoah River. This is the Seven Bends area here. And notice how the river pays attention to the geology too, right? It meanders within the shale. It does not venture too much into the limestones because it's a little bit harder to erode those rocks. So it kind of stays in its lane, as it were, as it's moving along. This is just an example to show you how the deformation can affect the weathering and erosion and the formation of the landscape. This is looking southeast east towards the Blue Ridge Mountains here in the distance, and this is a little gap, so it's a place where the mountain kind of comes down. This is called Harshberger Gap here, and this is actually near the ski resort area as well. But this gap is here, we think, because there's a fault. There's a planar break in the rocks, and you can see that pretty clearly here. There's a ridge, a resistant ridge of sandstone that comes down, and then it just stops, right? And then if you walk this way a little bit, hey, there it is again, and it's coming down here. So that's a place where the Earth's crust has been broken, things have been moved, and that created a weakness. It would be just like breaking your arm or your leg, and the next time you get injured, maybe that's a place that might be a little more susceptible to injury. Okay, these next few slides are kind of illustrating how variable our soil development is in this part of Virginia. Again, if you were to go out to the Piedmont or the coastal plain and randomly go to 100 different places, you would probably find a lot of consistency. But in this part of Virginia, I don't think that that's true, because you can go from something like this, where you have the Millboro Shale with no soil at all, almost zero soil development, to something like this in Waynesboro, where you have this really thick accumulation of clay and silt, a really well-developed soil profile. You can also find places where there are a lot of rock outcroppings and relatively thin soil. This is a relatively pure limestone called the Newmarket limestone, and so there's just not a lot of residue after the rock weathers that's left behind. Most of the rock is limestone, so it just goes away with the water, so you don't develop much of a soil on this kind of limestone. And then this is, again, another transported soil. This is one of these fan deposits. You can see lots of cobbles and things in here. Okay, very different, right, than the residual soil, that red clay soil that I showed you earlier. So that's just 4 random places, but I could show you even more variability than that. Okay, so this next part of the talk is really talking about how natural conditions affect us in terms of building and developing areas, and also in terms of making us choose to do certain things in different areas. So the natural conditions here in the valley that I've been talking about make some areas more suitable for particular land uses. For example, if you're driving around the valley and you're looking at where farmers are planting row crops, very often you see those crops on loose materials, on floodplain and terrace deposits of sand and silt. And I picked this sample. This is this photo up near Newmarket, and you can just see very clearly how the land use, this is a boundary between a terrace and no deposit, and between a terrace and the modern alluvium. And you can see how the land use change almost corresponds exactly with that boundary. And here's a great place. Here's a row crop field, and here's a pasture, and it's literally, the farmer figured all that out right long before I showed up and said, hey, that would be a much better pasture than a place to plant crops. Often where we see cattle grazing when we're driving around the valley, almost, I wouldn't say always, but often, most often, that's on residual hills and slopes developed on limestones and shales in the Great Valley Province. Not that you won't see a cow on a terrace or a floodplain, you certainly do. It's just 8 times out of 10, they're probably going to be a residual slope. That's also where much of the hay is made in the Shenandoah Valley. Many of the towns in the valley were developed at least partially on terrace deposits. This is Front Royal here. This is a bend in the river. Of course, the river itself was a major reason these towns developed, but I suspect that the availability of stable, elevated, relatively flat land surfaces played a role in site selection as well. I've noticed that most of the campgrounds in the Shenandoah Valley are on what I call fan deposits. They're not on residual slopes. And I just kind of casually the other day counted up 9, all 9 of these near us. This is Waynesboro, Stanton, Harrisonburg here. All 9 of these are on fan deposits, which is pretty interesting. The reason is that it's generally in a wooded area, gentle slope, easy to get around. This is just one example. This is Camp Shenandoah, where my kids went when they were in scouting. And almost all the campsites out here are built on the fans, just because they make nice campsites. Town parks, ball fields tend to be in floodplain areas. This is Purcell Park in Harrisonburg, just as an example. I guess I should just mention, well, why? Well, it's flat, If it's a soccer field or something, you don't have to do a lot of grading. Plus, if you have a flood and soccer field gets flooded, it's bad for the game, but it's not going to cost somebody a tremendous amount of money. Okay, we also have challenges based on the natural conditions in the valley. This is actually not a challenge. This is just the opposite in this picture. This is an old barn that literally built its foundation on bedrock, right? I mean, they took advantage of this outcropping of the Edinburgh Formation here, and they just used that as part of the foundation of the building. Now, for modern building, that doesn't work so good. Shallow bedrock tends to be a bigger problem. Usually you have to require some blasting if you're building a foundation or you're burying utility lines, et cetera. So that becomes problematic and expensive. It can be challenging if you have trying to site a septic system and you have shallow bedrock, or even putting in a sewer system. In areas that have shallow bedrock, there's just less availability for groundwater storage in the local area. And so depending on what kind of well you have, that could be a limiting factor for development. And if you're a gardener and your yard's full of rocks, it makes it a little hard to get a nice garden in there. In areas of soluble bedrock, that can, and when I say soluble, I mean limestone that can dissolve over time, that can create challenges. Groundwater in areas underlain by limestone tends to be a little more vulnerable to contamination. You always have the potential for sinkhole development, especially when you're changing land use in an area. And then some of the soils that develop on the limestone formations in this part of the valley are prone to shrink swell, and that can cause problems with building foundations, et cetera. When we talk about these areas that are overlain by the loose deposits, that can create issues. Some of those areas are unstable. They might have resulted from landslides in the past, and there are places where landslides could occur in the future. They can be challenging to excavate and keep a hole open if you're trying to put in a sewer line or something like that. And then they're definitely challenging for on-site septic systems. And then if you live on a real rocky spot, you might get your corn, as they said in the song, from a jar. This is just an example. This is Shenandoah County, Virginia's comprehensive plan. And they're just showing areas where there are limitations on development. All these areas are listed as severe limitations on development, and these are moderate limitations. So you don't see too many easy places to develop there, at least from the county's perspective. This is a similar map for Page County, but this is showing suitability for septic fields. And you can see the red is bad. so that's a challenging place, right, if you're a sanitary engineer or a soil scientist to try and find a good site for a septic system. Natural conditions also provide us with resources, things that we can use. The indigenous people certainly found useful things here, and we have over the past few centuries done a lot of mining of natural resources in this part of Virginia. This is a map showing areas where materials have been mined in the past, and it's not just random. You just can't go out anywhere and decide you're going to put a quarry in or a sand and gravel pit. You've got to have the materials, right? And that's determined by the geology. For example, you can see all of these red dots here. These are iron mines associated with a particular horizon in the Blue Ridge rocks. There's another similar horizon over here. All of these pinkish colored dots, these are limestone quarries. Okay. The green are lime mines that were used for agricultural purposes. Gas up here in northern Rockingham County. And then the yellow, it's hard to see on here, but all these dots are yellow, and they're all associated with those loose deposits of sediment. Just an example, this is a quarry that was used for stone to build I-81 up near 10th Legion, Virginia. And this is one of these fan deposits. This is just north of the Big Levels area, south of Stewart's Draft, and all of this loose material. This deposit is a few hundred feet thick. It's really impressive in its size. And so if you have rounded rocks in your yard, they're probably coming from this site, or there used to be a quarry near Grottoes doing the same thing. If you have square rocks, they're probably either coming from one of two quarries in Stanton here, most likely. Let's just talk for a few minutes about groundwater. Groundwater availability is really dependent on the geology in the area, specifically how many cracks and voids are in the area and how connected they are. That allows water to both enter the ground and also to be removed from the ground via a well. We find that wells installed in limestones and similar rocks typically have more water in them but they are more vulnerable to contamination. In the Blue Ridge, in the eastern part of the area, we find these rocks typically have lower yields for a variety of reasons, tend to have lower pH, but they're less variable in their quality. You don't see as much variation in that area. This is a map for a project I did just recently. This is looking at areas with these loose deposits, either fan deposits or terrace deposits. And we just discovered, just through a statistical analysis, this is the average well in an area that doesn't have a deposit. It yields about 10 gallons per minute, actually the median well. This is the median well in an area with a fan deposit, has twice the yield, typically the median well. And then in a terrace deposit, it doubles again. So that really, to me, has some significance if you're somebody trying to locate water in this part of Virginia. And then that western toe aquifer that I mentioned at the beginning of the talk, that's along the eastern edge of the valley on the west side of the Blue Ridge, and it's associated with these large fan deposits. Well, over time, the fans have chemically weathered the limestone below them, and then that limestone is dissolved, creating more room for more sediment. And over time, we've created these really thick packages of sand and gravel, and it makes a really important and great aquifer in this part of Virginia. And this is just a map showing Merck and Coors, and both of those facilities, as well as several facilities in Stewart's Draft, are there specifically because of that aquifer. And then the last little thing I wanted to point out, this is a new project I've just started playing around with some vineyards here in Virginia. How does the geology in the Shenandoah Valley affect the vineyards and the wine production in this area? This is just a map showing vineyards in this area. Okay. I just looked at this last week. Just statistically, about 70% of these vineyards are in carbonate bedrock. And that's really not that unusual. Probably that's not that far off of the percentage of area that's not national forest or national park that is carbonate. But the interesting thing is that the majority of them are just two formations: the Beekman Town, which is a dolomite, and the Conococheague, which is primarily dolomite. So I thought that was really interesting. Most of the remaining ones, including the Barren Ridge Vineyard, not too far from here, are in shale areas, and the majority are just in one formation. That's the Martinsburg Formation. And then there are two vineyards in the Blue Ridge that are underlain by that Catoctin basalt, and one by granite. And if you expand out beyond this area, there are actually a number of vineyards in the Blue Ridge that are in both of those units as well. Okay, so some conclusions here. I would say that deposition of sediment and magmatism have provided the raw ingredients of our lithosphere here in the Shenandoah Valley. That's kind of the way I think about it. Those are the raw ingredients that feed into our landscape and our area that we interact with. But then deformation changed the bedrock, and it also introduced structures such as faults and folds and cleavage planes and fractures, and that created the topography and the landscape in our area. More recent weathering and erosion shaped the landscape, created new deposits of sediment, opened those fractures up, created solution cavities, and it allows water to move through those materials and to be a resource for us. It also produces really variable soils in this part of Virginia. So this last little bit, the variability of the original bedrock, the locations of new deposits, and spatial differences in how much deformation has occurred, they produce this really diverse and interesting landscape that provides both challenges and opportunities for the residents here. Some acknowledgments, especially to the landowners here, and then I'm going to open it up for questions. Before I do that, I just want to point out, I always like this picture of this old barn because it shows the ability of the person who built this barn to recognize that this material here, this is a diabase boulder, one of these igneous rocks. They found that in their pasture, and I found it too, but it was half a mile from this barn, and they recognized it was a stronger rock, so they used it for the corner of that building. I thought that was pretty clever of them. So anyway, questions, I'm happy to try to answer them.
We have time for some questions, and if you would please wait for the microphone so the people online could hear.
Why is the water more susceptible to contamination in the limestone areas?
So in the limestone areas, we do have more thicker soil, more development of sinkholes. And so the source of the water that's coming out of your well is what we call the regolith, or the loose weathered material above the bedrock. And so there's less filtering if you have sinkholes that are providing conduits more directly to the bedrock. Yep.
All right, do we have another question? I think we have one right over here.
If you have a barn with a dirt floor, or you're building a house, where do you have to worry about radon?
So that's a good question. In the Shenandoah Valley, my understanding is that the shale units are most prone to radon production. Some of the limestones have some potential for that too. Really, the concern with radon is more when you have a tightly built structure, like a barn. Typically, that wouldn't be an issue because the radon is going to vent naturally. It's not going to accumulate. But if you built a home with a basement, really tightly constructed, and the air is going to stay there for a while, that's where radon can accumulate.
All right, I think we have one up front and then one in the back. Sir, hang on 1 second for the microphone.
I've enjoyed your presentation.
Oh, thank you.
What I'm curious about is I hike all over the Blue Ridge. I find huge boulders. When I say huge, they might be 40 feet across and 35 feet high. Mm-hmm. And they seem to be just set there. There's nothing else around them. Is it correct assumption that they were deposited by glaciers?
So it depends where they are on the slope. Further down the slope, that's a possibility. And in some very steep slope areas, I've definitely seen boulders that size that are part of transported deposits of material. But some of what we call the basement rocks in the Blue Ridge, just as part of the natural way that they weather, they have these kind of broad joint sets, and they'll actually just sort of weather in place, and you'll end up with these large sort of boulders. They've moved a little bit, but they're relatively in place. Yeah.
If I'm understanding you correctly, then they aren't put there by glaciers?
No, I don't think we have any direct evidence of glaciers in Virginia, certainly not in the last glacial period.
I just wonder how a 100-ton boulder, I come from a family construction people, would just be sort of set on the side of a hill.
Yeah, well, there are some large boulders that have moved by gravity. That's for sure.
They're
but
massive,
yeah, but there are some, as I say, that just sort of weather in place, and the soil has eroded away from around it. That
rock and so forth was washed away from around them.
well, the soil that developed on them, yeah, might have been eroded away. We do see that up in the Blue Ridge in the higher elevation areas, some large blocks that are just sort of sitting there relatively in place. Yeah. Yes.
More of a comment than a question, but two things on the dating. Any time I have a visitor to Waynesboro, I point at the Blue Ridge and I tell them that's the second oldest still in existent mountain range in the world, at 1 billion to 1.2 billion, the oldest being somewhere in southern Africa. Uh-huh. And then the other interesting date that you mentioned was the Native American deposits here to 12,000, which predates the breakup of the glaciers in Canada. Most of us are old enough to have been taught that the Native Americans walked here from Asia through Canada, but increasingly that 12,000 date, and it's showing up all over the Americas, indicates that at least the first wave of Native Americans came by boat, probably, since the glaciers would have basically been impossible to go over. They were so massive. If I had a question, so you mentioned how magnetism affects the area, but I always think of magnetism as being like a very broad thing, the North Pole, the South Pole, the magnetic.
I'm sorry, not magnetism, but magmatism. So that's the process of molten rock.
I'm sorry,
right?
I missed the word.
No
then.
problem.
Okay.
Yeah, but your question about the Blue Ridge brings up an important point. So the rocks in the Blue Ridge are really old, but the latest research suggests that the mountains themselves are actually not that old. We think there's been uplift in this area in the last 10 or 15 million years. So if you were here 20 million years ago, you might have been able to walk across that area and it wouldn't have been a mountain range at all. That mind blow. We were all taught in school, right, the oldest mountain range that's been weathered for so long, but the latest research suggests that might not be the case.
I think we have one more question here in the back, but I just want to point out that I think Matt and maybe some of our volunteers will also stick around to answer some questions one-on-one. So,
Thank you, Matt, for your presentation. You haven't mentioned precious metals or gemstones for the romantics among us. Are there any in the valley to
So
look
this
for?
is a great example of how geologic conditions affect your hobbies. If you like to collect fossils, this is a great place to do it. If you like to collect gemstones, not so much. We really, just because of the geology. Now, in the Blue Ridge and on the east side of the Blue Ridge, we have rocks like unakite that are semi-precious stones that wash out. But in the west of the Blue Ridge, gemstone collecting is not a very likely to be a very successful endeavor for you. Yeah.
all right, I know I said one more question. We had an enthusiastic hand over here. We're going to do one more.
In your research and your contemporaries' research, have you ever seen an evidence, not of just finding meteors, but finding an impact of a meteor in the valley?
Not in the valley. We have folks bring in rocks that look like meteorites all the time, but we almost thought we had one within the last year, but in 20 years I've been there, we've never actually had one come in. And I'm not aware of any evidence in this part of Virginia of meteorite impact. But there was a meteorite. Somebody was just telling me the other day in the Smithsonian, they have one that was found near Stanton back in the 1800s that's on display at the Smithsonian. So meteorites have landed in this area, but in terms of an impact crater, I'm not aware of one. Yeah.
Matt, we want to thank you so much for your time, and we want to thank the South River Watershed Coalition for all their support, and the Center for Cold Waters Restoration for making all of this possible. So let's please thank Matt Heller one more time, and we hope to see you next year at our spring version of our lecture series.